Welcome to our presentation. Our presentation is talk about Bigtable, which is a distributed storage system for structured data. We have 9 parts of this presentation. The first is the introduction. The following is the data model and API. The last part I will talk about the building blocks. The next part, my group mates Jimmy Xiao will talk about implementation, refinement, and performance evaluation. The last part, another group member, Ziyi Zhou, will talk about the real applications and the conclusion. So let's move to the introduction. Bigtable is a distributed storage system for managing structured data that is designed to scale to a very large size, petabytes of data across thousands of community servers. Despite this variety demands, Bigtable has successfully provided a flexible, high-performance solution for all of these Google products. In this presentation, we describe the simple data model provided by Bigtable, which gives Silence dynamic control over data layout and format. And we describe the design and the implementation of Bigtable. Bigtable has achieved several goals: wide applicability, scalability, high performance, and high availability. Bigtable is used by more than 60 Google products and projects, including Google Analytics, Google Finance, Occurred, Personalized Search, Writely, and Google Earth. Parallel databases and main memory databases have achieved scalability and high performance, but Bigtable provides a different interface than such systems. So let's talk about the data model. It has 3 attributes of it: rows, column families, and the timestamps. The row keys in a table are arbitrary strings. Every read or write of data under a single row key is atomic, a design decision that makes it easier for Silent to reason about the system's behavior in the presence of concurrent updates to the same row. Additionally, the row range of a table is dynamically partitioned. Each row range is called a tablet, which is unit of distribution and load balancing. The column keys are grouped into sets called column families, which form the basic unit of access control. All data sorted in a column family is usually of the same type, which must be created before data can be stored under any column key in that family. After a family has been created, any column key within the family can be used. What's more, its names must be printable, but qualifier may be arbitrary strings. In addition, access control and both disk and memory accounting are performed at the column family level. Each cell in a Bigtable can contain multiple versions of the same data. These versions are indexed by timestamp. Bigtable timestamps are 64-bit integers. They can be assigned by Bigtable, in which case they represent real time in microseconds, or be explicitly assigned via Silent applications. Different versions of a cell are stored in decreasing timestamp or order, so that the most recent version can be read first. To make the management of version data less onerous, we support 2 per column family settings that tell Bigtable to garbage collect cell versions automatically. The third part will talk about the API. The Bigtable API provides functions for creating and deleting tables and column families, as well as provides functions for changing cluster, table, and column family metadata, such as access control rights. Bigtable supports several other features that allow the user to manipulate data in more complex ways, which can be used to perform atomic read, modify, write sequence on data stored under a single row key. So the last part I will talk about is the building blocks. Bigtable is built on several other pieces of Google infrastructure. Bigtable uses the distributed Google file system to store log and data files. A Bigtable cluster typically operates in a shared pool of machines that run a wide variety of other distributed applications, and Bigtable processes often share the same machines with processes from other applications. Bigtable depends on a cluster management system for scheduling jobs, managing resources on shared machines, dealing with machine failures, and monitoring machine status. So my group mates Jim Xiao will talk about the following parts.
I will start with the second part. First, we talk about implementation. Actually, the Bigtable implementation has three major components: the library, and the master server, and the tablet servers. Actually, the library is linked into every client, and the master server is responsible for assigning the tablets to the tablet servers and detecting the expiration of tablet servers, also balancing the tablet server load and garbage the collection of file in GFS. And the tablet server manages a set of tablets. And then I will talk about tablet location, just like the plot shown in the slides. The first level is the file stored in Truby that contains the location of the root tablets. The root tablets contains the location of all tablets in special metadata table. Each metadata table contains the location of a set of user table. And then I will talk about tablet assignments. Actually, each tablet is assigned to one tablet server at a time. And a tablet server will stop serving its tablet if it loses its exclusive lock. And then the master is responsible for detecting when a tablet server is no longer serving its tablet and resigning the tablets as soon as possible. So by doing this, the master will periodically ask each tablet server for the status of its lock. And then I will go in with the tablet serving. Actually, the tablet is stored in GFS. And if you want to do the updates operation, the recently update will store in memory in a store buffer called memory table, and the older updates are stored in a sequence of access table. And if you want to do the operation, the write operation and or the read operation, the tablet server will check the operation is whether it's well formed or not, and also the tablet server will check the sender whether it's authorized to do the mutation. After that, after the satisfies both condition, the tablet server will do the operation. And the compaction is includes three parts. The first part is minor compaction, which is when the memory table size reaches a threshold, the memory table is frozen and a new one is created, and the frozen one is converted to an access table and written into GFS. The merging compaction reads the contents of a few access table and the memory table and writes out the new access table. The merging compaction rewrites all access table into exactly one access table, and that is called a major compaction. Well, the implementation is require a number of refinements to achieve the high performance, and the refinements has three methods. One is the following method is locality groups, compression, caching for read performance, and Bloom filters, commit log implementation, speeding up tablet recovery, exploiting immutability. And the seventh part is the performance evaluation. Actually, we set up a Bigtable cluster with n tablet server to measure the performance and scalability of Bigtable. And first, we will start with the single tablet server performance. We will evaluate the performance from the six aspects like the plot shown in the slides. They are random reads from memory table, random writes, sequential reads, and sequential writes and scans. And then we will put the throughput increased dramatically by over a factor of 100 as we increase the number of the tablet servers the system from 1 to 500. And the next part will up to my group member Ziyi Zhou.
Okay, let's we talk about the real application, and there are three examples. The first one is Google Analytics, and the second one is Google Earth. The last one is personalized search. As of August 2006, there are 388 non-test Bigtable clusters running in various Google machine clusters, with a combined total of about 24,500 tablet servers. The Google Analytics is a service that helps webmasters analyze traffic patterns at their websites. And the Google operates a collection of services that provides users with access to higher resolution satellite imagery of the world surface, both through the web-based Google Maps interface and through the Google Earth custom client software. The personalized search is an opt-in service that records user queries and clicks across a variety of Google properties such as web search, images, and news. So we take the conclusion. We have found that there are significant advantages to building our own storage solution at Google. We have gotten a substantial amount of flexibility from designing our own data model from Bigtable. In addition, our control over Bigtable's implementation and the other Google infrastructure upon which Bigtable depends means that we can remove bottlenecks and inefficiencies as they arise. Thank you. That's the end.